Okay, welcome back. Our next topic is gravitational potential energy. You might be saying, wait a sec, we know what that is. UG equals mgh. Well, for very big objects, we actually have this defined differently. When we're dealing with objects like planets and moons and stars, we actually have this defined a little differently. And you can see this on the reference tables. You're just going to have to know when to use this. The gravitational potential energy for very big objects is UG equals negative G little m big M over R, where G is the universal gravitational constant, little m is the smaller mass, big M is the bigger mass. Notice that you need two objects to have gravitational potential energy, and R is the distance between the two objects. I promise you that this actually can be shown to be equivalent to mgh, but it's going to be more useful when we are clearly dealing with objects that are really big. We're not just finding the potential energy of something that's on Earth. If we're finding the potential energy, the gravitational potential energy stored between like two objects out in space, like a planet and its moon, or a planet and a star it goes around. One of the interesting features here is the negative. The negative is there so that at infinity, at an infinite distance away, think about if R was infinity, if R was as big as could possibly be. If R is as big as can possibly be, I don't care how big your two masses are, if the distance between them is infinite, then there's zero gravitational potential energy stored. That's what this equation says. At infinity, there is UG equal to 0 joules. Essentially what we're looking at here when we're talking about gravitational potential energy is this is supposed to tell us, it helps us to determine how bound an object is, or a system is. By bound, we mean that the system will remain together. Think about the Earth going around the sun. The Earth is not just going to suddenly wander off and stop going around the sun. It's going to stay in place. The Earth is what we would call a bound system. Now consider something that just kind of passes near the sun, interacts with it for a little while, but then just goes shooting back off into space. Those types of objects exist. Okay? If it's not in a bound orbit, then the gravitational potential energy being, well, the gravitational potential energy is still going to be negative, but that there will be something different about the total energy of the system in that case. So gravitational potential energy is a measure of how bound a system is. Let's practice calculating it. It's very straightforward. Planet with a mass of 9 times 10 to the 26 kilograms orbits a star with a mass of 4.1 times 10 to the 29th kilograms at a distance of 7.2 times 10 to the 10th meters. What is the gravitational potential energy of this system? Well, UG equals negative G little m big M over R. Make sure you don't write R squared because that would be incorrect for gravitational potential energy. 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Mass of both planets, or a planet and a star, 9 times 10 to the 26 kilograms times 4.1 times 10 to the 29th kilograms over 7.2 times 10 to the 10th meters. The gravitational potential energy stored in this system is as follows. 6.67, I'm going to make that negative, times 10 to the negative 11th, times 9 times 10 to the 26th, times 4.1 times 10 to the 29th, divided by 7.2 times 10 to the 10th. We get a gravitational potential energy stored in the system of 3.42, we'll call it, times 10 to the 35th joules. That's how much gravitational potential energy is stored in the system. If you're worried about it being negative, just think about it like this, okay? The gravitational potential energy can be whatever we want it to be because we can set 0 to be wherever we want. With this equation, what we have done is we have set the 0 to be all the way out at infinity. And the reason for that hopefully will be apparent when we go and start talking about total energy. Really quickly, what would happen if the planet orbited closer to the star? What if it was farther away? What if it was infinitely farther away? Well, if it's closer, R is going to be smaller, and so this number is going to be, the magnitude is going to be bigger, but it's going to be more negative. So if it's closer, that leads to this being more negative, which we can interpret as more bound. It's going to be harder to get this object away from the star. It would have to have even more kinetic energy to leave that star behind. If it's farther away, the inverse is true. If it's farther away, there is the answer, the gravitational potential energy is going to be less negative. It's going to be closer to 0, and that means it's less bound. Okay, a farther away object, you don't need to have that object have as much kinetic energy for it to be able to leave the influence of that star altogether. And if it's infinitely far away, then what happens is the gravitational potential energy is 0 joules, and we would call this unbound. It's basically not even interacting if it's infinitely far away, and that kind of makes sense, okay? Then the force would end up being 0 as well. Yeah, the force would end up being 0 as well. Okay. We talk about gravitational potential energy because ultimately we want to talk about the total energy in a system. But before we can do that, we would have to talk about the kinetic energy. And before we can talk about kinetic energy, we got to talk about how fast something in orbit moves. So we've got to talk about orbital speeds. Orbital speed is very obviously the speed an object has in orbit. And a lot of times, for our purposes, those orbits are going to be circles. And that's really good because when we know if an object is moving in a circle, we know that it must be subject to a centripetal force, Fc. Low Earth orbit is a possible orbit around Earth that allows satellites to move around Earth without falling down, without crashing into the Earth. Low Earth orbit's upper maximum is 2 million meters above Earth's surface. If Earth's radius is 6.37 times 10 to the 6 meters and its mass is 5.97 times 10 to the 24th kilograms, how fast must a 200 kilogram satellite move in order to stay at this orbit? And what would the orbital period be? So two things. We want to know how fast it's moving in orbit. We also want to know how much time it takes to complete one orbit. Now, how are we going to go about this? We know that it's a circular orbit, and we know that the reason that the satellite is in a circular orbit is because the Earth exerts a force of gravity on it. So a good starting spot would be to do this. The centripetal force is equal to Fg. Now, I know that the centripetal force is equal to MAC, which could also be written, since AC is v squared over r, as m times v squared over r. I know that it's equal to the force of gravity. Since this satellite isn't on Earth's surface, we can't just use mg because we don't know what the acceleration due to gravity is out where the satellite is. So instead, we're going to use the big gravitation equation, the universal equation, g little m big M over r squared. Now let's go through what these variables are. This m in here came from the centripetal force equation. It's the mass of the object in orbit, the satellite. This little m is also the mass of the satellite because big M is the mass of the Earth. Those are going to cancel out. This r is the radius of the orbit. This r is how far away the two objects are. And if you think about it, the center of the orbit is the Earth. The perimeter is where is the satellite's path that it traces. The satellite is always going to be one orbital radius away from the Earth. So these r's are actually the same thing. Now, not in every gravitation question, that's not always going to be the case, but right here it is. So one set of these r's cancel out. And if you look what I have left, I have v squared equals g times big M, the mass of Earth, over r, the orbital distance from the satellite to the Earth. If I take the square root, I'm given this expression. V equals the square root of g big M over r. The orbital speed of an object in a circular orbit is only based on the mass of the planet it's orbiting, the mass of the body it's orbiting, I should say, and r, the distance to the center of the orbit, literally the orbital radius. That means I can find the speed very easily. The only thing I'm going to have to do first is I need to know what r is. How far away is this satellite from the center of Earth? That would be the center of its orbit. I know Earth's radius is 6.37 times 10 to the 6 meters, but the satellite's not on Earth's surface. It's 2 million meters above Earth's surface. So real quick, r is just going to be the sum of these two numbers, 6.37 times 10 to the 6 meters, plus that's 2 times 10 to the 6 meters. That gives me 8.37 times 10 to the 6th meters. So v is equal to the square root of 6.67 times 10 to the negative 11th newtons times meters squared over kilogram squared, and yes, you do have to write the whole thing, sorry, times the mass of Earth. Notice that the satellite's mass doesn't matter because it canceled out. That's very important. Let's see, 5.97 times 10 to the 24th kilograms over the distance. 8.37 times 10 to the 6th meters. And notice that the square root extends over the whole thing. Some of you guys get a little lazy and you make your square root look like it's just over the top. It's over the entire thing. 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th divided by 8.37 times 10 to the 6th. And I take the square root, don't forget that part. I get that the orbital speed of this satellite is 6,897 meters per second. That's extremely fast. That's going about 7 kilometers a second. That's like the distance from like Clayville to Chadwick's in literally 1 second. That's extremely fast. And notice, it did not depend on the mass of the satellite. Anything at the maximum of lower Earth orbit is going to be moving that fast. Now, I do need to know what the orbital period would be. Since it's a circle, we can actually use, it's always going to be the same distance away, so the speed's not going to change. We can use this. Speed equals distance traveled over time. Time is the period, that's capital T, that's what we're solving for. The distance is 2 pi r. I can rearrange this into T is equal to the distance of 2 pi times the radius over the orbital speed. I plug in 2 pi times 8.37 times 10 to the 6th meters, divide by the speed of 6,897 meters per second, and I end up with 2 times pi times 8.37 E6 divided by 6,897. I end up with 7,625 seconds for the period. And for a more useful measure, because no one ever counts that many seconds, this is about 2.1 hours. That's crazy. Something goes all the way around Earth in 2.1 hours. That's incredible to think about. Let's do the process again. Given the sun's mass as 2 times 10 to the 30th kilograms, Venus's mass as 4.87 times 10 to the 24th kilograms, and the average Venus-Sun distance as 1.08 times 10 to the 11th meters, with what speed does Venus revolve around the sun, and how long does it take Venus to revolve around the sun? Again, orbital speed, orbital period. We're going to do our derivation again. We start off with Fc equals Fg. Fc is equal to MAC, which is mv squared over r, equals g, little m, big M over r squared. The little m's are the mass of Venus. That's the thing that's actually orbiting. They will cancel. R is the radius of the orbit. R is the distance between the objects. Since Venus is orbiting the sun, they are also the same. And I'm left with V equals g m over r, where m is the mass of the sun, the object that's getting orbited, and r is the distance between Venus and the sun. 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. 2 times 10 to the 30th kilograms. And that's all over 1.08 times 10 to the 11th meters. The speed of Venus in its orbits, and you can look this up and it's going to be almost exactly what we found, is 35,145 meters per second. 35 kilometers per second. It's like going from here to Rome, Sequoia to Rome, in 1 second. Rome, New York, that is, not Rome, Italy. That's insane. Notice that the mass of Venus played no role. Okay? Again, we can find the orbital period by realizing that it's a circular orbit. V equals d over t. So the period equals 2 pi r over v. The period is therefore 2 pi times 1.08 times 10 to the 11th meters divided by 35,145 meters per second. The period oh, I did that wrong. 2 times pi times 1.08 E11 divided by 35145. What am I doing here? 2 times pi times 8 divided by 35145. I know what I'm doing. I'm sorry. This was right all along. Okay, the time ends up being, let's see, that's 1, 2, 3, 4, 5, 6, 7, 1.93 times 10 to the 7th seconds. No one knows how much time that is. If you were to unit convert, you would find that that's approximately equal to 223.5 days. And again, if you look up the orbital period of Venus, it does take about that long to go around the sun. Now, we did all of that, found the orbital speeds, not only because it's useful, but also because I want to make a larger point about orbital energy. That point is going to start like this. In a bound system, or in a bound orbit, the total energy, ET, that's an ET, is always negative. Okay? If two objects are bound together and will remain orbiting for forever, then the total energy is negative. If the two objects are not bound together, then the total energy is either 0 or positive. So let's take a look at Earth and Sun. The Earth and Sun are a bound system, so we should expect the total energy to be negative. If Earth's mass is 5.97 times 10 to the 24th kilograms, and the Sun's mass is 2 times 10 to the 30th kilograms, and the Earth-Sun distance is 1.5 times 10 to the 11th meters, calculate the gravitational potential energy of the Earth-Sun system. Well, that's pretty straightforward. UG equals negative G M big M over R, negative 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Mass of the Earth, 5.97 times 10 to the 24th kilograms. Sun's mass, 2 times 10 to the 30th kilograms. Distance between them is 1.5 times 10 to the 11th meters. I don't know why I put that in parentheses. It's not squared. That's fine. UG ends up being negative 5.31 times 10 to the 11th meters. Okay, let's remember that. Let's compare that to the kinetic energy of the Earth. In order to know the kinetic energy of the Earth, we're going to need to know the orbital velocity of the Earth. We're going to do that just like we did up here. We start from this principle, Fc equals Fg, and yes, you should start from this every time. This is not an equation that's given on the reference tables. Therefore, you need to work on deriving it to fully show where everything came from. MAC equals mv squared over r equals g little m big M over r squared. Little m is the Earth's mass, that cancels. R is the distance between the two, and the orbital distance, those are the same. V is equal to the square root of gm over r. Now I'm just going to plug in 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared, times the mass of the Sun, the body that we're orbiting here, 2 times 10 to the 30th kilograms, over the distance between them, 1.5 times 10 to the 11th meters. Got to throw the whole thing under a square root. The orbital speed of Earth is as follows. (29,822 meters per second. We want the kinetic energy of the Earth, so we plug that into K equals 1/2 mv squared. 1/2, 5.97 times 10 to the 24th kilograms, multiplied by 29,822 meters per second. And we see that we get a kinetic energy of 2.65 times 10 to the 33rd. Oh, I had 33rd up here. I don't know why I wrote 11. That's dumb. 33rd joules. Why did I do that? It's joules. I apologize for that earlier. Now that's interesting. Look at this. It looks like the kinetic energy is positive, the gravitational potential energy is negative, and it looks like the kinetic energy is about half of the gravitational potential energy. So if I go to find the total energy of the system, we're going to assume the sun is stationary. It's just going to be the sum of the Earth's kinetic energy plus the gravitational potential energy of the system. 2.65 times 10 to the 33rd joules minus 5.31 times 10 to the 33rd joules. And we end up with a total energy of negative, I'm going to skip some of the rounding here, 2.65 times 10 to the negative 33rd joules. Interesting. It seems that the total energy is just the negative of the kinetic energy. And as a matter of fact, this works out for any circular orbit. I'm going to show you that right now. This is a very famous physics theorem called the virial theorem. I first learned about it in college, but you could probably use it here. For any system that we want to find the total energy of, if it's a circular orbital system, we're going to need to know the kinetic energy, we're going to need to know the gravitational potential energy. Kinetic energy is given by 1/2 mv squared. Gravitational potential energy is given by negative g little m big M over r. Now, remember v, we're going to find v by doing this. Fc equals Fg. MAC equals mv squared over r, which equals g little m big M over r squared. Cancel the m's, cancel one set of r's. V squared, I'm not going to solve for v, but I'm going to solve for v squared because that's what I have here, equals g big M over r. I'm going to plug that in here. So now I have 1/2 m g big M over r minus g little m big M over r. I could rewrite this as g little m big M over 2 times r minus g little m big M over r. If you remember anything about subtraction from middle school of fractions, you need to have the same denominator. So if I'm going to get the same denominator, I need to multiply this by 2 over 2. That's going to give me g m big M minus 2g little m big M all over 2r. Okay, I could split this up into two fractions, each with a denominator of 2r, then we'd be right back to this stage. G times m times little m times big M appears both here and here. This is kind of like saying x minus 2x, which gives us negative x. Total energy is negative g m little m, or big M little m big M, over 2r. That's the total energy. Notice that looks very similar to both the kinetic energy and the gravitational potential energy. The kinetic energy ended up being this term right here, g little m big M over 2r. And the gravitational potential energy we know is negative g little m big M over 2r. Or excuse me, over r. So we have the following relationships for an object or a set of objects in circular orbit. We see that the total energy is equal to the negative of the kinetic energy. Okay? The difference between total energy and kinetic energy is 1. The total energy is negative, the kinetic energy is positive. All the negative means is it's a bound orbit. These two objects are stuck together. Not physically stuck together, but they will remain in orbit together. The total energy and the gravitational potential energy are related by the total energy. This is simply half of the gravitational potential energy. So we have ET equals the gravitational potential energy divided by 2. They are both negative. Therefore, we can also conclude that the kinetic energy, the negative of the kinetic energy, is equal to the gravitational potential energy divided by 2. All these things taken together can simplify the energy for us in a circular orbiting system. This is known as the virial theorem. Are they going to ask you what the virial theorem is on the AP exam? Absolutely not. but it is kind of useful to know, and it's a neat shortcut that we've determined it applies to any circular orbit, no matter what two objects are in it. It applies to any bound circular orbit. The total energy is equal to the negative of the kinetic energy, and the negative of the kinetic energy is half of the gravitational potential energy. Okay, kind of a neat result. You get lots of neat results like this in astrophysics. Everything that we've done right now up to this point, I kind of term it's like baby astrophysics. You're just kind of playing around with how these systems actually work in real life. Now, it does get a little bit more complicated in real life because not every object or not every orbit is perfectly circular, but this is a really good foundation. Doing this sort of stuff will get us answers that are fairly close to what's actually happening, and we can predict things like orbital speeds and how much energy these systems have. It's really, really neat. We're going to finish up in our next video with escape speed, orbital shapes, and angular momentum as it applies to orbits.